In this video, we're going to diverge from what we've been talking about, the regular solids or the platonic solids, regular polyhedra, and we're going to look at a huge set of two-dimensional figures or graphs where Euler's characteristic formula also holds true. We'll have to define what vertices, faces, and edges are in two dimensions, but we'll find that defined properly, v plus f minus e is 2. Well, first of all, I should tell you what a planar graph is. A planar graph, let's see, I'll draw one. This would, here's a planar graph. That would be a planar graph. Or this would be a planar graph. But in either case, I have to give myself a starting ending point. I have to label with a dot each place that the graph crosses itself, so that those we will consider vertices. The starting point, the ending point, and any place where our graph crossed itself. So here the starting and ending point are the same point, and it crossed itself once. These are called planar graphs. They're smooth curves or curves that you draw without lifting your pencil, and where you label or you put a dot on every place that they cross each other and at the starting and ending point. And these graphs, we will look at the dots as vertices. So here we have 1, 2, 3, 4. So v is equal to 4 in this one. And the edges, if you retrace this, you see 1, 2, 3, 4, 5. The edges, there are 5 of them. Those are the little curves between two dots. And the faces we count as face 1, face 2, and the outside is face 3. So the faces are 3. And notice, vertices plus faces is 7, minus edges is 2. Okay, for this one here, we see that we have 2 vertices. And as far as edges, well, we started here. So we had 1, 2, 3. Edges is 3. And faces here, well, we'll have one face here, another one here, and the outside is always considered a face. In other words, the curve divides the plane, the whole plane, into 3 regions. It encloses regions 1 and 2, and then the whole outside is another region determined by that graph. So we would say faces, we'll call them faces, is equal to 3. Notice, vertices plus faces is 5, minus edges, 3, is equal to 2. So this is just 2 examples of planar graphs, and you see that vertices plus edges, plus faces minus edges is indeed 2. You might want to try this yourself just to be convinced that these planar graphs satisfy Euler's characteristic. We will prove it, but let's just try one more. You close your eyes and make any drawing you want, as long as you don't lift up your pen, and when you're done, you have to label the vertices. So I am going to do another one like this, and I will label my vertices everywhere I crossed myself, and the starting and ending points. And let's see, I'll use a different color and label my regions. I got a region there, I enclosed a region there, I enclosed another region, and another region. And if you consider the entire plane, this graph also determines the region outside of it. So that would be region 5. And let's count. We have the vertices, 1, 2, 3, 4, 5, 6. We have the faces, 5 of them. And we have the edges. Well, we need to count. Start here where we began. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. And sure enough, v plus f minus e is equal to 2. So we have another example, and we should be pretty convinced that this is true. But one of the beautiful things in mathematics is that you can actually prove it. You don't have to do too many examples when you decide something is true. Hopefully you can prove it mathematically that it's true for all. What we're doing here, or that we will do, is a mathematical inductive proof, mathematical induction. The first thing I want to prove without any doubt is that if we're just given any planar graph that does satisfy, this is I think similar to the one I drew at the beginning, any planar graph at all that satisfies Euler's characteristic, and we see here that v is equal to 4 and e was equal to 1, 2, 3, 4, 5, and the faces in this case were 3, and so we see that v plus f is 7 minus e, which is 5, indeed is 2. So given any planar graph that does satisfy Euler's characteristic, I want to show you what will happen if we add an edge. Now there's only two ways to add an edge. Let me add it in blue. One way to add an edge is to go to an existing ending or beginning vertex and just put an edge on like that. Now what did this do? This increased our vertices by 1. We added a vertex and we added an edge. It didn't change the faces. So we still see that this is true in this case. 5 plus 3 is 8 minus 6 is 2. So if we added an edge in that way, the planar graph, the resulting planar graph still satisfies Euler's characteristic. Now let me show you. I'll draw the same one, same planar graph that we started with there, and there is one other way that I could add an edge. I could connect these two, and there I've just added one edge. These are the only two ways to do it. Now in this case, let's see, let me pick a different color for this one. Let's say I added a green edge connecting the two dots. This time, instead of, well, the vertices are still 4. I didn't add a vertex. I connected two that we already had. The edges, yes, I added an edge, so my edges will be 6. And my faces, instead of having 1, 2, 3 faces, now I have 1, 2, and this closed off another face. So now I have 4. So my faces are 4. And I'll put a green check here. You can see vertices plus faces is 8 minus 6 is 2. Now keep in mind what we have proven is that given any planar graph that does satisfy Euler's characteristic, if you add an edge, the resulting graph with one more edge will also satisfy Euler's characteristic. So we're almost done. With that fact in mind, if we know that a connected graph or a planar graph with one edge satisfies Euler's characteristic, well then so does one with 2. But then so does one with 3. And so does one with 4. And in fact we could keep going forever by adding one edge. And so a planar graph with any number of edges will satisfy Euler's characteristic. All we have to do is verify that when there is one edge, it does satisfy the characteristic. So let's draw a graph with one edge. There's really only one way to do it. Oh no, there's two ways. That way, or I could do it this way, couldn't I? I could have the same starting and ending point. So there's two ways to draw a planar graph with one edge. In this case here, we have the edges is equal to 1, vertices 2, and it only makes one face. So faces are equal to 1. And we see that faces plus vertices is 3 minus 1 is 2. Theorem is satisfied. In this case, we have two faces. We have face 1 enclosed and the outside face. So vertices are 1, faces are 2, and edges, it was just 1. So again, vertices plus faces minus edges is 2. So Euler's characteristic is satisfied by a planar graph with one edge. Well, by what we just did before this, it's also satisfied by any planar graph of 2 edges, 3 edges, 4 edges, any number of edges. So what we have shown is that Euler's characteristic holds for all planar graphs, and you'll see why this is important when you look at the next video. So far in our class, in section 2.3, we did a proof, and may have been proof by contradiction, or a direct proof that there are infinitely many primes. And then in section 2.7 we did a proof by contradiction that the square root of 2 is irrational. And this time what we just did here is called proof by mathematical induction. And I don't expect you to memorize this, but it is a really cool way to prove statements about the positive integers, or statements made about all natural numbers. Our statement was a planar graph with n edges satisfies v plus f minus e is 2, where n is any natural number. That's what we just proved. And so here's an outline of how we did it. This statement I'm calling S of n, Sn, let's say, is true for all n. Well, we verified that if we had e equal to 1, the number of edges, if we had one edge, then Euler's characteristic was satisfied. And we also proved that if we started with any number of edges, say k edges, that if we add one edge, that new graph with one more edge also satisfied Euler's characteristic. Well, if that's true, and we showed that it's true when k is 1, then the statement is true about 1, so it's true about 2 edges, so it's true about 3 edges, it's true about 4 edges, etc. In other words, the statement holds true for all natural numbers n. This is a method of proof that is used often to prove statements about all natural numbers.